Last week we talked about estimation. We said in statistical inference there are two major things we do. One is estimation, one is hypothesis testing. And when we do estimation, often we do interval estimation, right? So like estimating proportion, we come up with the point estimate, the percentage. We also come up with the margin of error, all right? So when estimating proportion, we have a confidence interval for estimating proportion. And same thing for estimating mean of a distribution, right? We have a confidence interval, okay? So that's estimation. And the other things in statistical inference is testing statistical hypothesis. You have a research question, maybe related to a certain characteristic of a distribution. Maybe it's proportion if you're dealing with categorical data. Or it could be average. You like to understand average. That's a special value describing a continuous distribution. And you hypothesize those values and you want to test whether your statement is true or not true, right? So in that case, you will do statistical hypothesis testing, right? So that's what we are going to do today. Okay, so we're going to start with testing proportion, like we would start with that estimating proportion, the same thing, right? So we want to test for population proportion, right? This is a slide that you have seen before, right? So the population proportion notation we use is the P in the book, all right? Some books use pi. I like that, all right, but either way, okay. And in order to understand this population proportion, we will collect data from a sample. We come with a sample proportion, and I think you understand what's mean by P hat, right? It's a proportion of certain category of interest in the sample. And so if X is number of successes or number of individuals belong to a category of success, or in here is interesting, if you're interested in number of people, percent of people who have no insurance, X would be the number of people who have no insurance, right? Divide by the sample size n, you get the sample proportion. And we realize this. I showed you this example, right? If you code your data as 1 or 0, then the sample proportion is the same as sample mean, okay? And we learned that a central limit theorem that tells us sample size get large, sample mean is approximately normal, okay? Regardless of where the population is from, what kind of population. The population is distributed normally or not normally, it doesn't matter. The sample mean will be normal. And since in this case our data is 1 or 0, it's not normal. But if your sample size is large, sample mean for this kind of data will be normal, right? And sample mean is the sample proportion, so that means the sample proportion, that kind of statistic, also normal due to central limit theorem, right? So we learned that theorem. It helped us develop the confidence interval estimate for proportion, right? We're going to use that sampling distribution also to set up hypothesis testing procedure, right? So we know from the past week that the sample proportion, this kind of measure, is approximately normally distributed, right? And its mean is the population proportion if we know it. We don't know it, right? But if we know it, right, the mean for the distribution of sample mean is the population proportion, and standard deviation is this quantity, if we do know the population proportion. Okay. So that's actually an important theorem. This tells us a sampling distribution or probably model for the sample proportion, this statistic. So we use that actually to help us construct this confidence interval, right? And it's a simple formula. You practice that, all right? So you know it's easy, right? You just need to figure out the proportion from your data, sample size, and the z-score. If it's 95%, it's 1.96. You have that memorized, all right? So it's a very simple calculation. So the reason we can do that because of large sample, we can use this formula. We said that we need to follow the rule. Actually, I use 5 here, but some books use 10. In fact, my previous lecture used 10. I should correct this, all right? But some books use 5, some books use 10, okay? And we also try to apply this procedure when the proportion is not too small or too large. That means this p hat is not too close to 0 or 1. Right? Hope that makes sense. Right? That's a large sample condition. Okay. So we learned this. That's great. Okay. Now, in some book, they may tell you another formula. They say this formula is a little bit biased. Right? So there's an unbiased formula. A formula look like this. Right? It's pretty complicated looking. So in most of introductory statistics book, nobody bothered to talk about this. But there is actually an unbiased formula for estimating proportion using confidence interval. I'd just like you to know, right? You don't have to worry about this. I won't test you on that, right? But just thought you know that there is actually another version of it. Now, when you use SPSS, I didn't give you that. So in the class, I told you we use a T, confidence interval estimate for mean, right? Instead of that, just to approximate it, right? If you really do hand calculation, you find out the end result will be very close to each other. And remember, the T-score always larger than Z-score, so your interval will be always more conservative, right? So you can definitely sure that you have 95% confidence when you do the estimation, okay? Good. So that's what we did last time, right? Today we're going to talk about testing hypothesis. Now, if you look at the basic step in hypothesis testing, it's similar to the scientific methods that you learn in high school, in elementary school. There are 4 steps. Oftentimes, the instructor probably tell you 4 steps, right? First, you have to have a research question. Then you gather evidence, right, helping you to answer those research questions. And you set up some criteria and summarize the data and make decision. And after you make decision, you draw a conclusion about, right? So that's pretty much what you do in scientific method. And when you do statistical hypothesis testing, it's about the same. You first have a research question, right? A research hypothesis. And based on this research hypothesis, you go and gather data. Once you get your data back, you organize them. And you have some decision criteria you set there in order for you to decide whether the research statement is, the hypothesized statement is acceptable or not. And then draw a conclusion, right? Then some book give you 10-step approach to solve the problem. Some book give you 5-step approach to solve the problem, right? In my lecture, I'm going to give you a 4-step, so maybe one less step, right? It depends. Some book doesn't even give you steps, right? But anyway, I'm going to show you a 4-step approach similar to this, okay? So you may start with a question. Well, you do a pre-election study, right? You like to see whether the percent of people in favor of a certain candidate is 30% or not, right? So that's a research question, right? Like in some of you want to study what proportion of people who actually are wearing a red shirt, why is you or not, okay? So that'd be a statement. And you gather your data and you find out that, well, you have 25% out of the sample, right, you get. And 25% is different from 30%, right? But does that mean 30% is wrong? You don't know, right? Every time you take a sample, you're going to get different results. There's that sampling variability, you know that, right? And it also depends on sample size, how large a sample size you get, right? If this 25% is from 10 people, I don't think you're going to say that 30% is incorrect, right? But if this 20% is from 10,000 people, then you probably would say, well, maybe it's incorrect. 30% is probably not right, right? So it depends on the sample size. But the reason we do hypothesis testing often is because we don't really have large sample. So we don't have a good idea about, that population characteristic. But we want to use this small sample just infer, right, that population measure to see whether the statement is acceptable or not, right? Because that's all we have. If you really have really large sample, then you don't probably need to use this hypothesis testing. Usually hypothesis testing is for smaller sample situation. Okay? But anyway, so we gather these information and we're going to learn some procedure or some concept, right, for using the evidence to make conclusion about your hypothesis. Okay. So for hypothesis testing, the first step, we have research question, and we're going to convert research question to hypothesis. So the first step is actually procedure-wise, right, when you try to work on a problem, is stating the hypothesis. And there are 2 hypotheses. You always have to state these 2 hypotheses in order to complete your procedure. And the first hypothesis is this null hypothesis. Null means nothing, right? You know the meaning of null, right? So usually it's a hypothesis of no difference, no correlation, or equal to, like at the 30%, right? So proportion is equal to 30%, right? That's the so-called null hypothesis. So if you try to use a mathematical expression to denote or to explain this hypothesis, usually you have an equal sign if there is a value you're comparing with, right? Equal sign, either circular equal or greater than or equal, less than or equal notation in your null hypothesis. So for example, in that example I mentioned, if the proportion of people in favor of a candidate is 30% or not, the null hypothesis will be equal to 30%. Okay. you can use a math expression like this, P stand for the population proportion equal to 30%. Or you just write a sentence or a phrase, say the percentage of people who vote to a candidate A is 30%. Right? Either way is fine. Now, usually while you work on a problem, you like to just use a notation. It's faster, right? Just P equals 30%. Right? That's it. But if you prefer to write it out, that's good too. Okay? So that's a null hypothesis. Okay? And the other hypothesis is called alternative hypothesis, something opposite to null hypothesis. Sometimes we use, actually, by the way, the null hypothesis we use H subscript 0, right, to denote the null hypothesis. And the alternative is people use H1, so 1 and 0, right, success and failure, right? Or sometimes people use subscript A to denote the alternative, the first letter in alternative. Okay, so either one is good. So alternative is be something different from null. Okay, so in our null hypothesis, we say we can use exactly equal or greater than equal or less than equal, right? But in alternative, we would say not equal or strictly less than or greater than, strictly greater than. That's the kind of notation you would use, right? If you try to use a math expression to explain the alternative. So this could be one of the alternative hypotheses, right? So my null hypothesis, the proportion is 30%. Now this alternative is what? Not equal to 30%. Okay, or you write a sentence or a phrase, say the percentage of vote for A is not 30%. So it's not, right? It's something opposite to the null hypothesis. You always have to have these two hypotheses, right? Null hypothesis always involve an equal sign, right, for testing proportion. Alternative will be either not equal or strictly greater than or strictly less than. So there's no overlap between null and alternative. Okay? And this is the first step, right? If you've done this, you complete this, you finish 25% of the hypothesis testing procedure. Okay. Let me show you a few examples. Right? So here, there's a question. A researcher is interested in finding out whether percent of people in favor of policy A is different from 60%. So this is similar to what we had there, right? What's a null hypothesis? Proportion is 60%, exactly that 60%, right? That value you specify in your statement, okay? Although our interest is different from 60, right? So that usually, that difference, right, we reflect in the alternative hypothesis. Okay, there's a change. That's why we want to do this research. So sometimes the alternative hypothesis, we call it research hypothesis, because you believe there's a difference. Okay, does it make sense? Right, so it's pretty simple. Let's look at another example. And usually when you have test hypothesis like this, we're going to call the test, right, for this kind of hypothesis a two-sided test, right? Why is two-sided test? Actually, we would explain that later on in the class. Now, when we do these hypothesis testing, we usually will have a decision rule. Now, in situation like this, if I have a sample proportion observed, right, and that sample proportion is so large in comparing with the 60%, right? Large number on the right side, right? And we will reject the null hypothesis. Or if this number, sample proportion, is too small, small on the left-hand side, we will reject the null hypothesis. How large is large or how small is small? We're going to have some criteria set up there, right? Maybe 70% is too large, below 50% is too small, right? So we got to set up these 2 points to help to make decision, help us to make decision whether it's too large or too small, so that we're going to reject the null and accept the alternative. So the decision criteria are going to set on both sides of the 60, right? So we're going to say it's a two-tailed test, okay? We will go over that. Right? And this is another example. A researcher is interested in finding out whether the percentage of people in a community that has health insurance is more than 70%. Right? So people are interested in whether the percentage is more than, maybe in the past it's 77%, but now you believe it's more than 77%. So that's why you want to do the research, right? So what's a null? Proportion is 77%, no different than that value. And the alternative will be what? Reflecting this question, more than 77%, right? More than means we're strictly greater than 77, okay? Hope that makes sense, right? So you have these two hypotheses. Now you can have your alternative exactly opposite for the null hypothesis, exactly opposite to the alternative by using the less than or equal. That's fine. Some people do that. Okay. So you will see two different ways people state the null and alternative. I prefer this. It's simple. Okay. Also matches the actually concept behind hypothesis testing. You will see that later on. Okay. So hypotheses like this will lead to a right-sided test, because if you do have a sample proportion that's much larger than 77, then there's a likelihood that you will reject the null and accept the alternative research hypothesis. So that criteria is set on the right side of the distribution, right side of the 77. Okay. If large enough, right, larger than that value, then we're going to say the alternative is true, and you'll be able to make the decision. Right. So this is a right-sided test. So if you have a greater than, it's a right-sided test. Right. If you have not equal to, it's a two-sided test. Right. Of course, this next example is a situation that we have less than. So researchers is interested in finding out whether the percentage of bad product, right, from a manufacturer is less than 10% or not. Okay. In this case, null is 10%. The alternative reflecting this question less than 10%. Okay. Okay, makes sense. And this would be a left-sided test, right? When we later on we will talk about why this is left-tailed, and you understand, right? It's not hard to. And also, this is the way I tell students to memorize. If you still, it doesn't make sense how to choose a left side, right side, determine left side. You have a less than, that's left-sided test, or left-tailed test. L, right, less than, left-tail. Okay. So this is an important step. Anytime you do hypothesis testing, you need to have a hypothesis stated, right? So you know what kind of hypothesis you have, then you'll be able to make decision, right, from the data you collected and going through the test procedure. Right? So it's a very important step. Now, do you have any of those papers left? The paper that anybody got a copy of this? Everybody? Okay. So the one I give you, this is really just the same as these three statements, except for less than or equal or greater than, they're placed in a different place, right? So let's see. Let's look at the z-test, right? Because when we talk about hypothesis testing for proportion, in the book that we cover, it actually uses z-test. This is another test. There's another test. A z-test is for large sample. Okay, but anyway, so look at this first question here. This is the one that you see, z-test, right? That side. Okay. So if you look at this first question, it's a question similar to what you just saw, actually, but now it's about the percent of people in favor of policy is A is less than 60%. So in this case, what should be your null? What should be your alternative? What's the null hypothesis like? Talk about proportion, right? If it's null hypothesis, always what? Equal to, right? You can say proportion is equal to 60%, or say 0.6. 60% is 0.6. Right? What about the alternative? We're interested in less than. Let me have the light on upper. Okay. Then that'll be what? Less than, right? So less than 60%. Okay. What kind of test is going to be? Left-sided or right-sided? Left-sided, all right. Let's look at this one. The percentage of people in community that has health insurance is different from 77%. So it's different from 70%. Null hypothesis still 77%, right? The alternative will be not equal to, yeah. So what kind of test is it? Two-sided, yeah, okay. The third one, no, it's easy now, right? We're comparing with 10%, so the null is proportion equal to 10%. The alternative is greater than. So that's it, right? And that's a right-sided, left-sided? Right-sided, yeah. So that's easy, right? This is pretty easy. Okay, so that's how do you state hypothesis, and it's very important. You got to know what kind of hypothesis so you'll be able to make a proper decision when you do the test. Okay. So that's the first step. For those 4 steps that I mentioned, right? We're going to have 4 steps to solve this problem. First step is important, stating the hypothesis. And then next, after we have our hypothesis stated, we know what kind of question we're trying to answer. So we go gather data to help us to answer these questions, right? Our evidence, in this case. If you're interested in maybe proportion of people in favor of policy, right? So you do survey, and you want to have a representative sample. After you get your survey result back, right, you'll be able to use that to make decision, okay? And since we're estimating proportion or testing proportion, right, so you're interested in sample proportion. Okay, so when your data come in, your data will be categorical, yes or no, right, in favor or not in favor. Okay, and from there, you'll be able to get the sample proportion, which is your evidence. Now, the logic behind hypothesis testing will be this, right? You collect the evidence, you want to see whether the evidence is strong enough to disprove your null hypothesis. And so when you do this hypothesis testing, logic is this. You first assume null hypothesis true. And you want to see your evidence strong enough for you to reject this null hypothesis or not. That's the idea, right? It's like in judicial system, when people are on trial, you first assume this person is innocent. Then you try to collect evidence, right, to prove this person is guilty. Right? If you don't have yet strong enough evidence, then this person, right, still stay innocent. Is this person really innocent? I don't know, right? But I just didn't have enough evidence to prove that this person's guilty. Okay, but you have to make decision, the jury, right? You got to make decision based on the evidence you collect. Sometimes you make wrong decision. That's possible. But you do the best you can to collect the good information. Reasonable representative information in order for you to make the proper decision, right? So again, like the beginning of the class I mentioned to you, you always stay skeptical anytime you see some result because it's based on probability model, right? So you want to have good data. That's very important, right? Really good representative data. So when you make conclusion, you feel more comfortable, right? But still, there's a chance of making error, right? You need to know that, right? So that's the logic behind hypothesis testing. When we do hypothesis testing, we first assume null hypothesis true, okay? And we see whether our evidence is strong enough for us to reject the null hypothesis or not, okay? So that's what I'm trying to say, right? First assume null hypothesis true. That's why we need that null hypothesis stated right, in the beginning of the hypothesis testing. So we're going to talk about this first test, right? I'm going to do a 2-sided test first. So explain a 2-sided test. This is so-called, sometimes people call it one sample z-test for proportion, right? A test for proportion, and this is a large sample test. So the first step we need to do is what? Stating the hypothesis. Now, we want to find out whether the percentage of people who vote for A is different from 30% or not. So that's our research question. We convert that research question to these hypotheses, right? Now, when you're writing a research article, this could be just your research question, right? You don't have to write this down in your research paper. This is like on your paper, right? On your scrap paper, you try to work out this hypothesis testing procedure. So you convert that research question to some mathematical expression or whatever, right? Try to work that out, okay? So writing paper, you don't need this, but when in the procedure, when you try to do hypothesis testing, oops, you do need to write these down, okay? So the null hypothesis will be proportion 30%. Alternative is different from 30% because that's what we were trying to test, right? So you got that, you finish 25% of the problem. So then what we do then? We need to go and gather evidence. Okay, so we went out and collect data, and let's say I collect a sample of 100 subjects. Out of this 100 subjects, 25 of them in favor of policy A. What was that, policy A? Yeah, okay, I'll vote for A, right? And so we like to use this to understand, missed the head there. It's supposed to be a head. Let me see. Yeah, this would be supposed to be a head there, right? So using this, we can get the sample proportion, right? Actually, it's 25%, 0.25 is the sample proportion. Okay, so that's our evidence. Now, our null hypothesis is 30%. And we want to check whether it's different from 30% or not. We got a sample of 25%, right? Is that really saying that the proportion is so different from 30%? I'm not sure. Okay, so in order to understand that, first, I want to understand the sampling variability for this measure proportion. We got to measure 25%, right? Next time we take a sample 100, I may get 32%. Anything is possible. What's the probability model for that? Well, this is how we do it. We first assume the null hypothesis is true. If null hypothesis is true, the sample proportion has a sampling distribution that has a mean that is 30%, right? Because if null hypothesis is true, population proportion is 30%. Okay. We had a sample of 100. That's a relatively large random sample. So the sample proportion, this measurement should be normally distributed, approximately normally distributed, with a mean that's the same as the mean, the population proportion, right? This is the sampling distribution of the proportion, if you recall, the sample proportion. What's the standard deviation of this? We don't have a we do have a population proportion now, if we assume null hypothesis is true, right? The p is 0.3, so standard deviation for the sampling distribution proportion has a mean 0.3 or 30%. Standard deviation is square root of 0.3 times 1 minus 0.3 divided by 100. Does it make sense? Right, this is that theorem we mentioned earlier. Okay. So because we have a null hypothesis, we assume null hypothesis is true. So we have a specific sampling distribution of sample proportion, right? It's normal with a mean 30%. That's good. And standard error or standard deviation of distribution is about 0.05. So what we do then, we want to, based on that sampling distribution, we want to know how extreme our evidence is in comparing with that sampling distribution of the proportion under null hypothesis. So what we do, we calculate the standard score of the sample proportion that we observe from that sampling distribution, right, under null hypothesis. Am I making sense? Right? See where this sample proportion stand in that sampling distribution under null hypothesis. So we calculate the z-score for that sample proportion. We use sample proportion minus this p0 is really just a population proportion under null hypothesis, which is that 30%, right? Because we try to calculate the z-score for the sample proportion under null hypothesis. And the standard error, of course, is also the standard deviation, also standard deviation of the sampling distribution of the sample proportion under null hypothesis. So that's it, okay? You calculate that, you get a negative 1.09. So you have a z-score of negative 1.09. That tells us this sample proportion is about 1 standard deviation from the null hypothesis in the sampling distribution of sample proportion. Okay. So this is the sampling distribution of sample proportion under null hypothesis, right? The mean is 30%. And what we observe is 0.25. That's about 1 standard. My graph is not so good. This is probably a little bit closer, right? But anyway, you get the idea, right? So just by looking at 0.25, it's not helping so much. Usually what people like to do is convert and standardize it, right? So the mean standard has a 0, and this score is standardized to standard score. So we know that actually 0.25 is about 1 standard deviation from the mean and it's to the left. Now, 1 standard deviation from the mean to the left, do we consider that extremely different from, extremely far away from the 30% under null hypothesis? Well, we make the decision, right? You're the person who make the decision. You decide where the cut is, right? So usually what people would do, they would draw a cut, draw a line there. If the z-score is too large in magnitude, we're going to say it's too far away. Now, how far is too far? There is a rule, right? Remember I mentioned to you that 5% or 0.05, right? I said p-value less than 0.05, they're going to reject the normality, something like that. That's the thing there, right? So how do we decide where we draw the line? There's a way we do it. We call it level of significance. That's that 5% or 0.05 that I kept mentioning when we talk about testing of normality, okay? It's a probability. This is by definition. It's probability level, right, selected by researcher at the beginning of the analysis. And I define unlikely value of sample statistic if the null hypothesis is true. What it means is, if null hypothesis is true, right, this is actually the location when we standardize all the score, right, sample proportion. This will be the location, 0 will be the location of the mean under null hypothesis. Okay, Now, if you have evidence that's so far away from 0, that means the null hypothesis is not true. Okay. How far is so far? If that evidence lies in the tail alpha proportion of the distribution, then we say evidence extreme, right? Your evidence not supporting null hypothesis. And that alpha usually is set at 5% or 0.05. That's why I say, if you compare that p-value with 0.05. Okay. So if I have an alpha specified, in this case, in this example I mentioned, we have 25% and the z-score is negative 1.09. Okay. If you have z-score about negative 1.09 or positive 1.09, they're not really so far away if I set my alpha at 5%. Because if I set my alpha as 5%, this tail I have 2.5%, this tail I have 2.5%. What be actually z-score that help me to determine whether you are in the tail 5% of distribution? I think you know that, right? Negative 1.96 and positive 1.96. If you put a negative 1.96, positive 1.96, the tail area is 5%. Right? You remember that? Okay. And so this score here, we call it critical value, should have a negative 1.96 there, and this point should be positive 1.96. And negative 1.09 is actually not in the tail. So in that case, our evidence is not extreme enough. Okay, not extreme means we're not going to reject a null hypothesis. Right? So I hope that makes sense. Right? This level of significance is really just that 0.05 I mentioned. Right? In the decision criteria we use for testing normality. Now we're using it for testing proportion. Okay, so in our case, it would be like this, right? Since alpha is 5% or 0.05, okay, we're going to split it into two parts, right, to figure out where the cutoff is for us to determine whether our evidence is extreme or not. Okay, the reason we can find this cut immediately because we know this is a standard normal distribution, right? We standardize that problem, right? We originally have a normal distribution for proportion. We standardize it, okay? So we can easily see how our evidence is extreme enough or not, okay? So we have name for these two cutoffs. We call them critical values, CV, critical values. So this is called critical value approach. Once you have the alpha given, you can always immediately figure out the critical value. So if I tell you my alpha is 10%, then the critical value in this case would be negative 1.645 and positive 1.645. If you've been doing practice, you probably know that. Generally, I have these two numbers memorized, the 90% and 95%. Okay, so we will reject the number. If you have a situation like this, you have statistic, right? That standard score for the sample proportion. That's we call it test statistic. If that test statistic lies in either one of these range, we're going to reject a null hypothesis because your evidence is so extreme. Right? Your evidence is extremely different from null hypothesis. Then we will reject the null hypothesis. If not, then we don't reject null hypothesis. Now, in our case, actually, our statistic is what? Negative 1.09. They're not in the tail. Right? These tail, we have a name for them. We call them rejection region. So if your evidence lies in either one of these tails, you're going to reject the null hypothesis. These are rejection regions for rejecting the null hypothesis, right? Remember the center. Here, center is a location for the null hypothesis. Okay. So actually, you have a rejection region of both sides, right? We call this two-sided test. That's another way to see it. Right? So this is actually a two-sided test. Either your evidence is too far from the left or too far to the right, right? You're going to reject the null hypothesis. But it's not too far. It's actually within these two critical values. Right? So this is called critical value approach. This is different from what we did when we make decision in normality tests. In normality test, we use a p-value, right? We didn't see p-value here. Well, we will see a p-value. Actually, p-value approach is the approach that everybody uses. The critical value approach is good for people to understand the concept. Right? But nobody really uses critical value in practice. People use p-value. So you definitely need to know how to use a p-value approach to solve this problem. Okay, so what is p-value approach then? You got this test statistic over here, negative 1.09. Okay, what is p-value? P-value is when null hypothesis is true, right? The probability of observing an evidence that is as extreme or more extreme than the one that you actually observe. That probability is a p-value, right? So the probability of observing an evidence that is this extreme or more extreme, that will be this tail area, right? In fact, this is a two-sided test. If you have a number that is 1.09, that number have the same extremeness as negative 1.09, right? Extreme or more extreme. So you also consider area to the right of 1.09. Okay, and combine these two tail area, that's the p-value, right? So you check the standard normal table, you'll be able to find this tail area, and twice of that, actually, well, it round out for me, huh? Anyway, you know what I mean, right? Okay, so summing up these two tail area, I get 0.2758. That's the p-value. Okay. In this case, that's a p-value for the test, and the decision rule for p-value approach is really simple, awesome. It's always the same. The decision rule is always reject null hypothesis if the p-value is less than alpha. You know what the alpha is, right? Alpha is that 5% that we set as a decision rule. We call it level of significance for the test. So in the future, you may learn more testing, statistical hypothesis testing procedure. Regardless of what test procedure you're going to learn in the future, the decision rule, always this. You reject null if p-value is less than alpha. Always. Okay, we will learn t-test, we'll learn chi-square test. It's all the same. Right? The decision rule, always the same. Reject null hypothesis if p-value is less than alpha. And oftentimes the alpha is set at the 5%, 0.05 level. Okay. If you can't remember this rule, you should not pass this course. Or you can't apply this rule. It's the most simple thing, all right, to memorize, right? Reject null if p-value less than alpha. In the future, you may become a medical doctor or engineering right? And often you would try to read some paper to update your knowledge. And oftentimes, you know, when people do research, they collect data and they do this hypothesis testing. You will see p-value on all the articles. Okay, so you need to be able to determine, you know, what that p-value is about. Okay. I should say understand what the p-value is about. Okay. Good. So here we have a p-value which is these two tail area. Right. Add them up, we get 0.2758. It's actually higher than 0.05, so we're not going to reject null hypothesis. So this is actually a definition of p-value. I kind of just said it right earlier. And you realize, let me go back to this. If p-value is small, what does that imply? That implies these statistic is further away from zero, right? The further away this statistic from zero, the smaller the p-value will be. Right, the smaller the tail area will be, right? So if you have smaller p-value, that means you have stronger evidence for rejecting null hypothesis. Okay. The advantage of this is you need a p-value. If once you have p-value, you change the alpha level, I'm fine, right? I have this p-value at 0.2758. Okay. So if I decide I'm going to use 10% as the level of significance, fine. 0.27 is greater than 10%. I still not going to reject null hypothesis. Well, I changed my alpha level of significance to 1%. Again, 0.27, right? It's greater than 1%, right? You're not going to reject null hypothesis. So it's easy. If you take the critical value approach, you're going to have headache. Every time I give you an alpha, you're going to find a table, try to convert, then get the cutout, right? You see the inconvenience of using the critical value approach, right? P-value approach, you just look at that probability, you know how extreme your evidence is. Regardless of what level of significance you want to use for the test, you can just do that right away without looking up table. Okay, so that's why, you know, people don't use the critical value approach, use p-value approach. But critical value approach, like I say, it help you to understand the concept, right? Learning some procedure and understanding the concept. Okay, so now we can draw a conclusion, right? If you take critical value approach, you realize that negative 1.09 is not smaller than negative 1.96. So it's not in the rejection region. Right? It's in between negative 1.96 and positive 1.96. And also, if you take p-value approach, you find out the p-value is not less than 0.05. Okay. So we're going to say you do not reject null hypothesis. That's your conclusion, right? Now remember, when you're writing your answer, I'd like you to do it this way, right? When you also write the answer for a test. When you find out the p-value is higher than alpha, you're going to say, I do not reject null hypothesis. And if it's less than, you say you reject null hypothesis. Don't say you accept null hypothesis. Say reject or not reject. Okay, that's the language you use. Okay, if you don't reject null hypothesis, that doesn't mean null hypothesis is true. Okay, so be careful on that. Okay, so just say reject or not reject null hypothesis. And of course, a very important thing you have to do is the conclusion, right? You have that research hypothesis, you want to see whether it's different from 30% or not. That research hypothesis or alternative hypothesis, you have to comment on that. You want to say whether you reject or not reject null hypothesis, and you want to say whether your evidence support or do not support alternative. That's the language, support or do not support alternative. So here I say, I have sufficient evidence to support the alternative, or there's no sufficient evidence because you didn't reject null hypothesis. So there's no sufficient evidence to support the alternative that the percentage of vote will be different, significantly different from 30%. Okay? Does it make sense? Right, so you see, when we did this problem, we start with the hypothesis, right? We state the null and alternative hypothesis, and that is important because especially the null hypothesis helped me to figure out how I standardize the test statistic, right? Because of null hypothesis, we got this value help us standardize our statistic to be able to calculate the z-score, right? The test statistic value, okay? And because of that, actually, you know it's a z-test, right? And you know the test statistic, you know the sampling distribution. Because of the null hypothesis, you have the decision rule, okay? You can use that to help you to calculate the p-value based on the z-score, right? And of course, the third step is actually decision rule. You always take this decision rule, okay? But in order to use this decision rule, you have to calculate the p-value, right? For the two-sided test, once you have a statistic, you want to find this tail area multiplied by 2, right? If in case your statistic is actually positive 1.09, what will be the p-value? The same. If it's two-sided test, you find this tail area, because this is the same as this tail area, right? You find this tail area multiplied by 2. That would be your p-value. Right? It's a probability of observing an evidence that is as extreme or more extreme than the one that you actually observe. This is what you actually observe. Chance of observing evidence is as extreme or more extreme than that. Okay, this negative 1.09 and positive 1.09, they have the same extremeness. Both have the same distance from the null hypothesis. Okay, and so if you have this decision criteria with a p-value, you should be able to draw a conclusion. Right, so that's the fourth step. So step 1, stating hypothesis. Step 2, using the null hypothesis to compute the z-score. Step 3, figure out the decision criteria and the p-value. Step 4, draw a conclusion. Right? Your conclusion always say you reject or you do not reject null hypothesis, and also say you support or you do not support the alternative. Okay? You reject this, you support this. You do not reject, you do not support this. Okay? Okay, so keep that in mind. So these are the steps I just mentioned. Right? I think they're not too hard, right? Earlier, I actually showed you some questions, probably questions, when we study the sampling distribution. It's hard from there, right? This is more organized when you try to do hypothesis and you know the steps to go through. Okay. So when can we use this z-test? The reason we can use z-test because we have large sample. Just like the reason we can do that confidence interval estimate using z-score, right? The confidence interval formula is because we have large sample, okay? And large sample criteria will be the same as what we had earlier. Right? You expect each category you observe at least 10 counts. You wish the proportion to be far away from 0 and 1. Right? That's still the assumption. Okay. You know, sample size is too small. There are other tests for it. Right? There's a test called binomial test. It's based on binomial probability model. Okay. I think we will look at that later on when we're looking into nonparametric tests. Okay. So it's not that you have small sample. There's no way. There's a way, right? But you don't use this one. There's another procedure you can use. Okay. So let's look at the one-sided. we had a two-sided situation. Same data, how about if we do a one-sided test? So it's still the same data, okay? When we do the one-sided test, the difference is if we want to test whether the proportion of people who vote for A is less than 30%, right? If that's the case, you know, your alternative would be less than 30%, reflecting this research question, okay? And then it'd be the same evidence, the same, then we want to base on null hypothesis to come up with a sampling distribution or sample proportion. Then what we would do is actually standardize your test statistics still using the null hypothesis, just to figure out how extreme this 0.25 is away from null hypothesis. Okay. So these are the same. The only difference is the step 3, when you try to figure out how extreme this evidence is, because you are actually testing one-sided test. Right? So for critical value approach, you'll put that 5% all on the left side. Right? If you're doing the left side, if you want to test whether the proportion is less than 30% or not. So 5%, if you want to figure out cutoff that tail is 5%, you look at the Z table, right? Or the bottom row of the T table, if you remember, right? You'll find out that it's actually 1.645 if you look at the Z distribution. Okay? And so there's only one cutoff now if you're doing left-sided test. So if you have a Z statistic that is extreme and is less than negative 1.605, you will reject the null hypothesis, the rejection region on this tail. So this is why it's called a left-sided test. Okay, the decision criteria is set on the left side. Now, evidence actually negative 1.09 is not as extreme. It's not in the rejection region, so we fail to reject null hypothesis. So that's if you take the critical value approach, that's how you do it. Okay. If you take p-value approach, what you do, just need this tail area. Remember, p-value is what? Probably observing evidence that's as extreme or more extreme than this, right? Extreme in the sense that you reject null and accept the alternative, right? So it's read this left tail area. So if this whole thing doesn't make sense to you, right, as far as how to get that how to get the p-value, memorize this. If you have a left-sided test, right, once you find the location of test statistic, you find the error to the left of that statistic. That will be the p-value for your left-sided test, if you're doing the left-sided test. And how do you know whether you're doing the left-sided test or not? Look at your alternative hypothesis, right? If your alternative is testing whether the proportion is less than some number, it's a left-sided test, okay? And when you have your left-sided test, p-value will be the area to the left of your test statistic. It's pretty straightforward, I think, right? Okay. I hope you understand the concept, right? It'll be much better. So you found the area to the left of this, and that's a p-value, and the decision criteria will be what? You reject the null hypothesis. Same thing, reject the null hypothesis if the p-value is less than 0.05. Now, is this less than 0.05? No, okay? So you draw the same conclusion. The p-value is not less than 0.05, so you fail to reject the null hypothesis. That means there's no sufficient evidence to support the alternative that the proportion is significantly less than 30%. Making sense? I hope it's not hard. So the whole process involved, again, 4 things. First, stated null and alternative. Second thing is compute a z-score, right, based on your sample evidence, your sample proportion. And third step, calculate the p-value, okay? And once you have a p-value, you can always draw your conclusion, right? P-value rule is just simple. Reject null hypothesis, p-value less than alpha. And alpha can be 0.05, can be 0.01, right? So, okay, hope that makes sense. And again, calculating p-value depends on right side or left sided, right? If it's left-sided test, p-value would be area to the left of statistic. What if p-value for the right-sided test? Area to the right of statistic. So in this case, if I do a right-sided test, area will be this piece. This is a big piece. Oh, why do I still have that? Anyway, right? Ignore that. Only this area, right? So it will be what? 0.8621. That would be the p-value for right-sided test. So if I wish to test whether the proportion is greater than 30% or not, of course not, right? My sample proportion is 25%. There's no evidence to support that it's greater than 30%, right? So you expect the p-value could be very high. Sometimes you may, when you run SPS, sometimes you may see p-values, it's say 1.0. It's almost 100%. That's possible. Anything is possible, right? Okay. P-value is any number between 0 and 1. So any value between 0 and 1 is possible. It depends on the evidence. Okay. Cool. By the way, do you remember how to find this number? Use a t-table and the z-table. Okay. This is simple, right? Because the table that we have from the books always give you the cumulative from the left end, right? So it should be easy. Okay, good. That's good. So this is just telling you there's something that you shouldn't do. Okay. I've shown you the step for hypothesis testing. First is stating hypothesis, then collect evidence, right? And then set up decision criteria and draw a conclusion. Oftentimes people do this. They collect the data, right? And then test the hypothesis, and then look like, no, actually collect the data and kind of observe the evidence, and then decide what hypothesis they want to set. So the outcome always in favor of what they want to do. That's not right, right? It actually, this whole process is incorrect. Okay. Am I making sense? So, like I say, when you do your term paper, right, you want to define your question first, right? It's good that you haven't learned this hypothesis testing, right? So I ask you to kind of define some questions too. You want to see whether the proportion of people wearing red shirt is greater than 50% or not, right? You have that stated. And you come back and then collect the data, do this procedure, right? Test, state hypothesis and test hypothesis, and then draw a conclusion. That would be a proper way to do. If the outcome is just opposite of what you think, that's a finding too, right? You have a research question for some reason, right? So don't try to adjust the hypothesis later on, or adjust the research question, try to meet some research result that you like to reach. That's not a right practice, okay? Hope I'm making sense, right? Okay. So that's called data snooping, right? Don't pick on the data and then try to change your research question, right? That's not a right practice. And there are errors when you always, right, when you're making these decisions, right? There's so-called a type 1 error. What is type 1 error? Type 1 error is when the null hypothesis is true, but you reject it. That's possible, okay? You're taking a random sample, so anything can happen. Maybe the proportion is really 30%, but you just end up having 10% in your data. Can that happen? Yeah, that's possible. Okay, so if that happened, we say we have a type 1 error. Okay, and that is also why when we're making this decision, why we always, most of the time, people use 5% as a cutoff. Okay, if I use 10% as a cutoff, I have a higher chance to reject null hypothesis, right? But I will have higher probability of committing type 1 error. Am I making sense? Right? If null hypothesis is true, this is the distribution. Okay. If I draw my cutoff at here, I'm going to say anything, if I observe anything below this point, I'm going to reject the null hypothesis. You see what I mean? Right? The larger the further this draw closer to the center, the higher possibility of committing error. Right? So after years of practicing, people realize 5% is reasonable. Right? You don't want it to be too much, right? Higher than 5%. Some people actually go to the left end, use 1%. That's fine, right? But you don't want the type 1 error to increase by 10 or 20%. Nobody will accept your outcome. Since people have been practicing this hypothesis testing using 5%, if you suddenly use a 10%, people will have doubts on your result, right? Will question on your result. Okay, so in the future, when you go out and doing data analysis, right, try to use a 5% or less. And that's what people use. Okay. So that's type 1 error, right? When the null hypothesis is true, and you reject a null hypothesis, that's possible. Right? So that's why we didn't use too high alpha level. We usually use 5% or less. Okay. And there's also a type 2 error. When null hypothesis is not true, but we did not reject that. That's also possible. Okay. Now, we will talk about that in a little bit. This is related to sample size computation, right? Related to power of a test, how sensitive a test is in detecting a difference. Usually it's related to sample size too, so we will look at that in a little bit. Okay. So this is kind of a quick summary. When we do this one sample z-test for proportion, you will use one of these hypotheses. It depends on the research question, right? So each pair you should have a null and alternative. So you can decide whether you want to do a left-sided or right-sided test, okay? And then second step is compute the test statistic. Test statistic is what? Standardizing your sample proportion using the null hypothesis. Right? So null hypothesis, you have a proportion, population proportion there, right? And then you will use either p-value approach or critical value approach. You make decision, and again, as I said, most of people use p-value, right? And the decision rule is to reject null hypothesis p-value less than alpha. Okay. How do you calculate p-value? If you're doing two-sided test, p-value will be what? Twice of the tail area. Once you have a test statistic calculated, right, you know the location of it. Find that smaller tail, right, that side. Multiply that area by 2. That's a p-value for two-sided test. If you're doing right-sided test, and greater than proportion, greater than p0, right, greater than, the p-value is area to the right of your test statistic. If you're doing the left-sided test, p-value area to the left of test statistic. This little z is actually the actual z-score from the test statistic. Okay. And if you use critical value, then you have to use that alpha level to figure out the cutoff, right, and then compare your z-score with critical value. But I'd like you to really know how to do this one, p-value. Okay. Then, of course, step 4, draw conclusions. Right, so that's all. Yeah, that's right. So maybe, do I have so? Oh, yes, I do. Okay, so let's look at it again. Look at another one. Here is another example. A researcher hypothesized that the percent of people living in the community who has no insurance coverage during the past 12 months is not 10%. So this guy believed it's not 10%. Okay, so he surveyed 1,000 individuals from this community and found out 122 answered that they did not have insurance. Okay, so that's just a sample. And how can we use that to test this hypothesis, right? To see whether the actual proportion is significantly different from 10%, as this person's claim. Okay, so how do we do this then? First step, state the hypothesis, null and alternative, right? The guys say it's not 10%. So that's a research question, right? And no different from 10% always be the null hypothesis. And that not 10% will be the alternative. Okay. So we have the null hypothesis here, 10%, that help us to standardize the z-score. So the test statistic will be what? Your sample proportion, we have 122 out of 1,000, so the sample proportion is 0.122, right? Using that, standardize it by subtracting the proportion and the null hypothesis. This will be the P0. Like P0 is the proportion you specify in the null hypothesis. Right? So that's you just point 1, plug into all the P0, n is the sample size. So you put it in there, you get a z-score 2.32. And our alternative is not equal, so this is a two-sided test, right? So once you find this 2.32, you want to find the area to its tail, right, and multiply by 2. So 2.32, if you look up a z-table, is 0.0102. Right? Let me see. I have a table. Yeah, let's maybe check on this table together. We haven't looked at the table today, right? So let's look at this. So we have 2.3 to 2.3 and 2. 2.32. That's a cumulative distribution. Up to here is, right, 2.32, and the area is, cumulative is 0.98 and 9a. So its tail area is what? 1 subtract this, right? So it's 0.0102. Okay, because we're looking for this tail, right? We have a 2.32 there. Okay. Am I making sense? Okay. So that's how we get this 0.0102. Oops, taking a little bit. Okay. Right. Area to the right of 2.32 is this. Okay. But we're doing two-sided test, so we need to multiply that tail area by 2. So we also include the area to the left of negative 2.32, right? And that tail, the total area, is the p-value for two-sided test. So it's actually 0.0204. If we test the hypothesis at 5% level, then you will reject null hypothesis if this p-value is less than 0.05, right? 0.05, so it's actually less than 0.05, so you reject the null hypothesis. You reject the null hypothesis, that means there's sufficient evidence to support the alternative that actually the proportion of people who have no insurance in this community is statistically significantly different from 10%. Okay. Hope that makes sense? Okay. And you notice I say statistically significantly different from 10%. Right? That difference is tested by the probability model. So we statistically, right, conclude that the difference is significant. I hope that makes sense, right, based on the probability model. So there's actually a difference between statistical significance and practical significance. In practical sense, if you really, here your concern is the proportion of people who have no insurance, okay? Let me see. Okay, this is my data, 0.122, okay? So it's about 12%. That's what I observed. Now, the actual population proportion, in this case, actually, let me see. We rejected the null hypothesis, right? If I reduce the sample size to 100 instead of 1,000, what would be the z-score? Let me try this. I didn't do this. I've never done this before. Let me try that. Right? That'd be fun to see. So we had a 0.25 and subtract 0.3. Okay, I'm using Excel to do this. So square root of 0.3 times 1 minus 0.3 and divide by 100. Okay, let me see. Okay, if that 0.122, that 12% was from sample 100. The z-score, hold on, let me see. What did I do? Not 30, right? 10%. My mind still stay in the previous problem. Okay, so that's 10%, right? So that may be different. Oh, wow. Is that right? So if I reduce my sample size to 100 instead of 1,000, the z-score becomes 0.73. So if you have a z-score 0.73, what would be the p-value? Would the p-value greater than 0.05 or less than? P-value would be greater than 0.05, right? Let me draw a picture. Okay, let me show you this. Earlier, when we sample size 1,000, we get a z-score of 2.32, right? When we have sample size 100, this is based on proportion of 0.122, right? Become 0.733. If you happen to have a sample of 100 instead of 1,000 and produce that sample proportion, sample of 100 give you non-significant difference, right? 0.77, this area definitely is what? Larger than 0.05. Okay, so sample size actually affect the outcome. When the sample size is larger and larger, it brings up the significance. The larger the sample you get, the more likely you get significant outcome. Okay, so the significant difference you found here is based on that probability model. It's affected by sample size too, right? So once you found this significant, it's so-called a statistical significant. That's why I use the term statistical significant in there. Okay. Years ago, there was a physician from St. E. asked us about a research result that he got. He tried to test all different variables in his study and found out all the variables are significant. He asked, why? Everything is significant. And we asked him, how large a data you use? He said, about 30,000. I said, wow, that's huge data. If you have 30,000 pieces of data, if you want to test for mean, every time you test, you're going to get a p-value that's so small because you have very large data, right? When you have very huge data, actually the actual descriptive statistical measure, like a mean or proportion, will be good enough, very good information. It should be very close, right? If this is a representative sample, it should be very close to the true population. The testing hypothesis may not be that useful. Okay. And so what I try to mention is this significant is statistical significant. Okay. Sometimes you find statistical significant, but in practical sense, the difference may not be significant. That may be happening too, right? You want to make a important decision about a certain drug that you have developed. Okay, you find out that the proportion of people that have improvement is significantly different, statistically significantly different from the cutoff you drawn there. Okay, but it's based on the sample. The larger the sample you get, again, the more likely you're going to see that difference. Okay, but that difference may be very small, but because of having very large sample, that's just the nature of this test. It would tell you that you have a significant difference. But that difference may be just 0.1%. Because you have 10,000 cases in there, it says significant. You see what I mean, right? So that difference may not be practically significant. So you got to know what's the difference between the two, right? While you're making decision. I hope I'm making sense, right? The statistical significance are actually affected by the sample size. Okay. All right. Anyway. So if that's any question for that example, does it make sense to you? And the concept behind hypothesis will be also very similar to this. If you understand this, right, I think it's not too hard for you to understand the t-test or chi-square test, whatever test that you're going to learn in the future. Right? It's always similar. You have a hypothesis stated. You want to state that null, understanding what's a null hypothesis is especially important because that null hypothesis helps us to set up a decision criteria, the sampling distribution that we will use for testing hypothesis. For anything, when we learn t-test, it will be the same. You have a null hypothesis. That null hypothesis help you to set up a sampling distribution for decision making. When we learn chi-square test, again, there's a null hypothesis there. Use that null hypothesis, again, set up sampling distribution of a specific test you use for that hypothesis testing procedure. Right? So it's the same. The concept is very similar. Right? We learn confidence interval. Okay. Now, when we construct confidence interval, we use the same sampling distribution, same kind of sampling distribution. Right? So this is actually confidence interval estimate for percentage of people who smoke from 2 different regions. Right? This is based on the 1,500. This is based on 2,100, 2,000. Right? This is the number of people who smoke. So you have from the community A, 36% smoke. Community B, 32% smoke. Now you know how to calculate confidence interval, right? Once you have these data, you should be able to calculate confidence interval estimate for percentage of people who smoke. So I got from A confidence interval is this, B confidence interval is this. you know how to calculate it now, right? We learned it earlier. Okay. So assuming that I have these two confidence intervals, but plot them on the real number line. This first group has an interval from here to here. The second group has an interval from here to here. Right? They don't overlap. Okay. Usually if you see things like this, that kind of indicates the actual proportion of smoke between these two populations are not the same. Statistically, they're different, is significant. Okay, sometimes we can use a confidence interval kind of testing hypothesis. This is kind of a hypothesis testing for difference between two proportions, right? Percentage of smoker in two populations. Okay. Sometimes people can also use this one confidence interval to actually make inference for the proportion of people who smoke in population A or not. If I claim that the percentage of people who smoke in population is 30%, I got a confidence interval like this. What does that imply? Do I reject the 30% hypothesis or not? If somebody says the proportion is 30%, but I get a confidence interval like this, does this interval or your statistics support the 30%? No. So you will reject that, right? So sometimes people actually use confidence interval to do hypothesis testing. Of course, if you do that, you can report a p-value, right? P-value is something that people use to read, and when they read articles, they like to read that. But sometimes in some of the research, the objective is not read testing hypothesis. What they do is just do the estimation. But if you're a reader, you have different objective, right? You really like to test hypothesis. When you see this confidence interval, you should be able to use that to conclude too, right? Because that interval doesn't cover the proportion. Right? So you see some people say that, wow, there are actually 3 different methods, or at least 3 methods for hypothesis testing. One is critical value approach, the traditional approach, right? Using cutoff, which is something that we definitely won't use. You don't see that often, right, when people present the outcome. The other is the p-value method that everybody uses when they write the article. Right? And sometimes people actually also use a confidence interval method. Right? If you're reading an article, people didn't report your p-value. When you see the confidence interval doesn't cover the value that you hypothesize, that means you're rejecting that. Right? The proportion is not that well as that number. Right? Based on the confidence level you use in hypothesis test, in confidence interval estimate. If you use 95%, okay, you can say, well, at 5% level, right, comparable to the 95%. Okay, that's when you're doing two-sided tests. Okay. But this is just for you to know, right? But when you do the test, always take the p-value approach. When I ask you a question on hypothesis testing for proportion, always use p-value approach. Okay. Okay. Good. Any questions? Do you have any questions? How about let's try this? These things that I've shown you here. How about this one? We have these 3 things, right? Let me see. Yeah, okay. So let's try this first one. Researchers are interested in finding whether well, we keep doing this policy here. Let's change to something else, right? Let me see. Bad product, maybe this. Researchers are interested in finding out whether the percentage of bad product is greater than 10% or not in the manufacturing. Right? So we know it's right-sided test. After you stated this, you know it's right-sided test. Okay. So you need to collect evidence. So assuming that I take a sample of size 400. Okay. And out of the 400, let's say 30 of them. Oh, 30 is not. Well, 30 is possible. Well, maybe give you a 30. So 30 out of the 400 will be the sample proportion that are defective. If you got that data, can you complete this test? So let's try that. Okay. The goal is to see whether the percentage of bad product is greater than 10% or not. Okay. And you got a sample of 400, find out that 30 of them bad product. Well, actually, just by looking at that number, you know it's not supporting greater than, right? Supporting the other side. But I'd like you to go through it, right? Regardless. Find a z-score, find a p-value, and draw a conclusion. Right? See if you can do that. Let's try that. And hope you have brought your z-table, right? From now on, you should always bring some tables. Z-table, T-table, chi-square table. Right? These are tables they like to bring to class so that you can use them for class practice. So you got that copy, right? Let me flip back to the formula or example so you can follow an example to do this. How about this one? You have the data copy, right? 30 out of 400. So you should be able to follow this. It's different though, right? The hypothesis will be different, okay? Because you're testing whether it's greater than 10% or not. Okay, so it's different hypothesis now.